Hello everyone, welcome to Kanitha Maths channel. In today's video, we will be discussing CBSE Class 10 Maths Chapter 2 Polynomials. We have 4 sections: Introduction, Geometrical meaning of the zeros of a polynomial, Relationship between zeros and coefficients of a polynomial, and Summary. So in your previous class 9, you have studied polynomials. You have studied only one variable polynomial, and also you have discussed about the degrees of the polynomial. So let's have a quick recollection of that. So polynomial is defined to be a mathematical expression which consists of variables, constants and exponents, and all these terms are combined using mathematical operations such as addition, subtraction, multiplication, division. And it should be noted that division involving variables are not considered to be polynomials. So example for polynomials are 5x square minus 2, 3t square minus 2t plus 1, 24 y power 8. So all these are examples for polynomials. So the term polynomial itself tells that it consists of many terms combined using the mathematical operations, and we can also perform the basic arithmetic operations such as addition, subtraction, multiplication, division by using these polynomials. And depending upon the number of terms involved in the polynomials, they are classified as monomial, binomial, trinomial, quadrinomial, etc. So in general, polynomial is expressed using this notation p of x, and polynomial is defined in general as an x power n plus an minus 1 x power n minus 1 plus an minus 2 x power n minus 2 plus etc. plus a1x plus a0, where x is the variable in which the polynomial is expressed. That is why we represent the polynomial as p of x, and a1, a2, a3, etc., an are all coefficients of the polynomial, and all these coefficients can be real numbers in general. But if I specifically consider only natural numbers or only integers or only rational numbers, then we call them to be integer polynomial or rational polynomial, etc. So now moving on to the idea of number of terms. The first one is monomial. If you have only one term in the polynomial, then we call that to be monomial. An example for that is 2x square, 5t minus 8 yt. So here in all the polynomials we have only one term got involved. So this is considered to be monomial. The second one is binomial. If your polynomial consists of two terms, then we call that to be binomial. Example for that is 2x minus 5, 8a power 2 plus 12y x y square plus 3x. So in all these polynomials we have only two terms got involved. Therefore all these are considered to be binomials. Next one is trinomial. If the polynomial consists of three terms, then we call that to be trinomial. So example for that is 4x cube minus 2x plus 8, 5x square minus 9x plus 2. So all these terms have all these expressions have 3 terms, therefore we call them to be trinomials, right? So in a similar way, if the polynomial consists of 4 terms, we call it as quadrinomial, and 5 terms we call it as pentanomial, etc. Right? So the next idea that we are going to discuss is degree of a polynomial. Degree of a polynomial is defined to be the highest power of the variable x in the polynomial. For example, if you take this, here the highest power involved is 2. Here also the highest power involved is 2. Though we have t power 1, but t square is the highest. Similarly, here the variable y has the power 8. So the degree of this polynomial is 2, and this is 2, and this is 8. So here they have given few examples. 4x plus 2. Here the variable x has the power 1. Therefore the degree is 1. Here the power is 2. Highest power is 2. Therefore the degree is 2. Similarly, in this expression, we have the highest power to be 3. Therefore, the degree is 3. For this, we have the highest power to be u power 6. So, 6 is the degree of this polynomial. So, whatever the variable your polynomial is expressed, doesn't matter. The highest power of that variable is considered to be the degree of that polynomial, right? As I said earlier, the expression 1 by x minus 1 got divided by the variable x. Therefore, this is not a polynomial. The next one is root x plus 2. Here we have the power of x to be 1 by 2. But in a polynomial, the power should be a positive integer. Since 1 by 2 is not an integer, this is not considered to be a polynomial. And the last one is 1 divided by x square plus 2x plus 3. Here also, the expression got divided by the variable. Therefore, this is also not considered to be a polynomial. So, depending upon the degree of the polynomial, we classify them to be linear, quadratic, cubic, etc. So, let us discuss that. If your polynomial is of degree 1, then we call that to be linear polynomial. And they have given few examples: 2x minus 3, root 3x plus 5, y plus root 2, x minus 2 by 11, 3z plus 4, 2 by 3, u plus 1. So, here we have the degree of the polynomials involved are all 1. Therefore, this polynomial is considered to be linear polynomial, right? And if your degree is 2, then we call that polynomial to be quadratic polynomial. So here they have given few examples. So here the power of the variable x is 2, therefore it's a quadratic polynomial. Similarly here, and the third expression, everything has the degree to be 2. Therefore, all these polynomials are considered to be quadratic polynomials. And it should be noted that the coefficients of the variables are in general real numbers. So, we no need to worry about the coefficients. They can be rational numbers, irrational numbers, whatever it is. We only concerned about the highest degree of the variable involved in that polynomial, right? So, similarly, if we have the highest degree to be 3, we call that polynomial to be cubic polynomial. And here they have given few examples. The highest degree in all the polynomials are 3. Therefore, we call this these polynomials to be cubic polynomials. And the general form of all these polynomials are given as, first one, linear polynomials. The general form is ax plus b, provided a is not equal to 0, because if a is equal to 0, then the degree will become 0. Therefore, this is not a linear polynomial. Similarly, quadratic polynomial has the general expression to be ax square plus bx plus c with the condition a not equal to 0. The next one is cubic. So the general form is ax cube plus bx square plus cx plus d with the condition a not equal to 0. Because when a becomes 0, then the degree of the polynomials got reduced to the lower orders. Therefore, they should be not equal to 0. And you may ask the question why b, c, all these are and it is to be noted that the coefficients of x square in the cubic polynomial and the constant terms not necessarily should be not equal to 0, because even if they get 0, the degree remains to be the same. So the highest derivative, sorry, the highest term coefficient should be not equal to 0, right? So now they have considered a polynomial p of x equal to x square minus 3x minus 4. So if they put x equal to 2 in this polynomial, they are getting the value to be minus 6. So this minus 6 is the value obtained by replacing the variable x by 2. So the value of the polynomial when x equal to 2 is minus 6. In a similar way, you can substitute any value for this variable x and you can determine the value of the polynomial at that particular x value, right? So here also they have substituted one more value for x, that is x equal to 0, and they have obtained the answer to be minus 4. So in general, if p of x is a polynomial in x and if k is any real number, then the value obtained by replacing x by k in the polynomial p of x is called the value of the polynomial at x equal to k, and we denote that as p of k. So easily we can determine the value of the polynomial for any x value, right? And here they have given one more example. So they have considered a quadratic polynomial x square minus 3x minus 4, and if they put x equal to minus 1 and x equal to 4, they are getting the values to be 0. So polynomials, when their value becomes 0 by substituting particular values for x, then that particular values of x are known to be zeros of the polynomials, right? So here they have considered a quadratic polynomial, and by putting x equal to minus 1 and 4, they are getting the values to be 0. Therefore, minus 1 and 0 are called zeros of the quadratic polynomial what we have considered, right? So 0 of a polynomial is a real number, say k, such that p of k equal to 0. That is, when you substitute this k value in the place of the variable x in the polynomial, you should get the answer to be 0. So any real number, if you substitute in that polynomial and if you get the value to be 0, then that real number is known to be 0 of a polynomial. Fine. And in class 9 you have studied how to determine the linear zeros of a linear polynomial. It's very simple. You have the linear polynomial. It's very easy for us to determine the zeros. So simply we can replace the variable x by k so that you will get ak plus b, and we want the answer to be 0. So we are trying to determine the 0 of that polynomial. So p of k equal to ak plus b equal to 0. So when you rewrite this, you will get the value to be k equal to minus b by a. So in general, for a linear polynomial ax plus b, the 0 of that linear polynomial is given by minus the constant term divided by coefficient of the variable x. So thus we can easily determine the 0 of a linear polynomial, and this 0 will depend on the values of the coefficients, right? Coefficients of the variable x. So let us consider one more example. So if you take a linear polynomial, say 5x minus 2. If I want to find the 0 of this linear polynomial, as per the definition, it should be equal to minus constant term divided by coefficient of x, that is minus of minus 2 divided by 5. So the answer should be 2 by 5. Can also be written as 0.4. So if you want to verify this, if you simply replace this x by this value, you should get the answer to be 0. So the polynomial what I have considered is 5x minus 2. So in the place of x, if I replace it with 2 by 5 or 0.4, whatever it is, you should get the answer to be 0. So when I cancel this, I'll get 2 minus 2, which is equal to 0. So what I have estimated is correct. Fine. Next, moving on to the section 2.2, geometrical meaning of the zeros of a polynomial. Mathematically, we can determine the zeros of a polynomial. Not only for linear, we can also determine the zeros for any degree polynomial. But what is the geometrical interpretation of these zeros? That we will discuss in this section. So in this section, we are going to concentrate only on linear and quadratic polynomials. So here they have considered a linear polynomial, say y equal to 2x plus 3. In your previous class, you have studied that the geometrical interpretation of a linear polynomial is a straight line. So the graphical representation is a straight line for a linear polynomial. So here they have obtained a straight line for this linear polynomial 2x plus 3. Now we have to identify the zeros for this polynomial, right? So in order to determine that, they have determined 2 points through which this straight line passes. So here they have estimated minus 2 comma minus 1 and 2 comma 7. So when you substitute the x values, you can obtain the corresponding y value. So you can randomly pick any value for x, and if you substitute in this expression, you can obtain the corresponding y value. So you can select those 2 points, and if you plot those 2 points on the graph, minus 2 comma minus 1 will be here, and 2 comma 7 will be here. So these 2 points lie on the straight line y equal to 2x plus 3, right? Fine. Now in the graph you can see that this straight line intersects the x-axis at only one point, that is minus 1.5 comma 0, right? So at x equal to minus 1.5, the straight line intersects the x-axis. So this value minus 3 by 2 or minus 1.5 is considered to be 0 of this polynomial, right? So if in order to draw a straight line or the graphical representation of the linear polynomial, we have to estimate at least 2 points which lie on this straight line. So you can randomly pick any 2 values for x, and you can correspondingly determine the y values, and using those 2 points you can draw the straight line, and then you can identify the point of intersection of the straight line on the x-axis, and that corresponding x value will give you the 0 of that linear polynomial, right? So in general we have discussed that for a linear polynomial of the form ax plus b, provided a is not equal to 0, the 0 of that polynomial is given to be negative of the constant divided by the coefficient of x. So in the geometrical representation, we can identify the 0 of the linear polynomial or the straight line corresponding to the linear polynomial will intersect the x-axis exactly at one point, which is given by minus b by a comma 0. Fine. Next, we will discuss the geometrical representation of the zeros of quadratic polynomials. So here they have considered a quadratic polynomial, say x square minus 3x minus 4. The graphical representation of a quadratic polynomial will be a parabola. So here they have given the graphical representation of the quadratic polynomial. So in order to draw the parabola, we need the x and y values. So they have randomly chosen the values for x, and the corresponding y values they have obtained by substituting the x values in the quadratic expression. So by plotting all these points, say minus 2, 6, minus 1, 0, 0, minus 4, etc. They have finally obtained a parabola which is upward open. And now you can identify that the parabola intersects the x-axis at two different points. One is at minus 1, 0 and another one is at 4, 0. So exactly at 2 points the parabola intersects the x-axis. So these two x values, say x equal to minus 1 and x equal to 4, are said to be zeros of this quadratic polynomial, right? And for a quadratic polynomial, we can consider three different cases. The case 1 is the graph cuts x-axis at two distinct points A and A dash. So in the graph 1 and 2, you can easily see that the parabolas, whether it is open upwards or open downwards, they are intersecting the x-axis at two different points, and thus they are having two zeros. And case 2 is the graph cuts the x-axis exactly 1 point, that is at two coincident points. So thus we have a 0, the value is same, but it will get repeated twice. That is, we will have a 0 for the polynomial which will be repeated. Case 3, here the graph is either completely above the x-axis or completely below the x-axis. That is, the parabola will never intersect the x-axis, which means there will be no 0 for the parabola or the quadratic polynomial what we have considered. So in general, for any quadratic polynomial, we will have three different cases. Either we will have two distinct zeros, or we will have only 1 0 which will get repeated, and the third one is no 0 for the quadratic polynomial. Next we will consider a cubic polynomial, say x cube minus 4x, and they have given a tabular column where the x and y values were given. Randomly you can select the x values and the corresponding y values are determined, and when you plot the points you will be resulted with this graph. From the graph you can observe that this graph coincides the x-axis at three different points: minus 2, 0, 0, 0 and 2, 0. So for the x values minus 2, 0 and 2, the graph intersects the x-axis. Therefore, we have three zeros for this cubic polynomial. Fine. They have also considered two more cubic polynomials, x cube and x cube minus x square, and their corresponding graphs are given in the figure 2.7 and 2.8, which you can see here. So here you can observe that this graph corresponding to y equal to x cube intersects the x-axis at only 0. For the figure 2.8, that is for the function y equal to x cube minus x square, the graph intersects the x-axis at two different points, 0, 0 and 1, 0. Therefore, at two different x values, 0 and 1, the graph intersects the x-axis. Therefore, for this cubic polynomial, we have 2 zeros, whereas for this cubic polynomial x cube we have only 1 0, right? Thus from the above examples we can observe that for a cubic polynomial we can have at most 3 zeros. Thus for a linear polynomial we can have at most 1 0, and for a quadratic polynomial we can have at most 2 zeros, and for a cubic polynomial we can have at most 3 zeros. We cannot have more than that. So for a polynomial of degree n, it can have at most n zeros, right? So that is what they have given in this remark. And next one is example 1. Look at the graphs in figure 2.9 given below. Each is the graph of y equal to p of x, where p of x is a polynomial. For each of the graphs, find the number of zeros of p of x. So in graph 1, so in the first figure, the graph intersects the x-axis exactly at 1 point, therefore the number of zeros is 1. And here it intersects at 2 points, so 2. Here it intersects the x-axis at 3 points, 3. Thus we have the number of zeros for the figure 1, 2, 3 to be 1, 2, 3. And for the fourth figure, the graph is a straight line, but it intersects the x-axis at only 1 point. You should not get confused that it is intersecting the y-axis. We are concerned only about the intersection of the graph with the x-axis alone. Therefore, here the number of intersection is only 1. Therefore, only 1 0. Here again it is 1. Here we have 4 intersections. Therefore, for the figures 4, 5 and 6, we have 1, 1 and 4. Right? Next, moving on to the exercise 2.1. Question number 1. The graphs of y equal to p of x are given in figure 2.10 below. For some polynomials p of x, find the number of zeros of p of x in each case. So they have given the graphs corresponding to the polynomials p of x. They may be linear, quadratic, cubic, whatever it is. We need to identify the number of zeros of the polynomial for each case. Number 1, we have a straight line. So this straight line is parallel to the x-axis, but it is not intersecting the x-axis at anywhere. Therefore, the number of zeros for this polynomial is 0. Moving on to the case 2, here the graph intersects the x-axis exactly at 1 point. Therefore, the number of zeros is 1. And for the third case, it is intersecting at 3 points. Therefore, the number of zeros is 3. And for the fourth case, we have the graph intersecting at 2 different points. Therefore, the number of zeros is 2. And for the fifth case, it is intersecting at 4 different points. Therefore, number of zeros is 4. And for the sixth one, 1, 2 and 3. It should be carefully noted that here it is intersecting at only 1 point. Here also it is intersecting at only 1 point. Therefore, the total number of zeros for this case is 3. Right? Next, moving on to the section 2.3, relationship between zeros and coefficients of a polynomial. So, in the previous section, we have discussed that for a linear polynomial of the form ax plus b, the zeros of the linear polynomial is given by negative of the constant term divided by the coefficient of x. So, it's very easy for us to identify the zero for this linear polynomial. Now, in this section, we are going to concentrate on how to determine the zero for a quadratic polynomial. In your previous class 9, you have studied how to factorize a quadratic polynomial. So, it's a very simple idea. Suppose if you have a quadratic polynomial, say 2x square minus 8x plus 6. So, what we used to do is, we try to factorize this so that the sum of the roots will be equal to negative of the middle term, and the product of the roots will be equal to the constant term. So, thus they have determined the factors for this quadratic polynomial to be 2 into x minus 1 into x minus 3. And when you try to identify the zero for this polynomial, we obtain the values to be x equal to 1 and x equal to 3. So from this we can observe that sum of its zeros will be equal to negative of coefficient of x divided by coefficient of x square, and product of zeros will be equal to constant term divided by coefficient of x square. So it is to be noted that when you determine the zeros for the when you want to determine the zeros for the quadratic polynomial, so these two expressions will help us to identify them. So always remember sum of its zeros will be equal to negative of coefficient of x by coefficient of x square, and product of its zeros will be equal to constant term divided by coefficient of x square. So here they have considered one more example by considering a quadratic polynomial 3x square plus 5x minus 2. Now they have determined the factors for the quadratic polynomial by using the method of splitting the middle term. So now they have determined them to be 3x minus 1 into x plus 2. Now they want to determine the zeros. So by equating both the factors to 0, they are getting the values to be x equal to 1 by 3 and minus 2. So now if they verify the above expressions, we obtain sum of its zeros to be equal to minus 5 by 3, which is equal to negative of coefficient of x divided by coefficient of x square, and the product of the zeros will be equal to minus 2 by 3, which is equal to constant term by coefficient of x square. So in general, alpha star and beta star are the zeros of the quadratic polynomial ax square plus bx plus c with the condition a not equal to 0, and if we have the factors for the polynomial to be x minus alpha and x minus beta, then alpha plus beta will be equal to minus b by a, and alpha beta will be equal to c by a. It should be noted so that we can solve the problems using this idea. Next, moving on to example 2, find the zeros of the quadratic polynomial x square plus 7x plus 10 and verify the relationship between the zeros of the coefficients. So now they have factorized the quadratic polynomial and they have obtained the factors, and by equating them to 0, we are getting the x values to be minus 2 and minus 5. And now if we verify their relation, that is sum of the zeros, if you add minus 2 and minus 5, you are getting minus 7. Minus 7 can also be written as minus 7 by 1, where 7 is nothing but the coefficient of x and 1 is the coefficient of x square. Thus, it satisfied the expression, and the product of zeros, minus 2 into minus 5 is 10, 10 by 1. So 10 is the constant term and 1 is the coefficient of x square. So thus we have verified the relation between the zeros. Example 3, find the zeros of the polynomial x square minus 3 and verify the relationship between the zeros and the coefficients. So now they have expanded this x square minus 3 by using the identity a square minus b square equal to a minus b into a plus b. It's very simple. So in the place of a we have x, and in the place of b we have root 3. So x minus root 3 into x plus root 3. So by equating them to 0, we are getting the values of x to be root 3 and minus root 3. They are the zeros for the given quadratic polynomial, and if we verify the relation between the roots or the zeros of the polynomial, we are getting the sum of zeros to be 0, because a negative of coefficient of x, here we don't have the x term, right? So the coefficient of x here is 0, where the coefficient of x square is 1. So the sum of the zeros is 0, and product of the zeros, root 3 into minus root 3 will give you the answer minus 3 by 1. That is, minus 3 is the constant term and 1 is the coefficient of x square. Thus, we have verified the relation between the zeros. In example 4, find a quadratic polynomial, the sum and the product of whose zeros are minus 3 and 2 respectively. So here they have not given the quadratic polynomial, but by using the relation between the zeros, we can determine the quadratic polynomial, right? Here they have given the sum and product of the zeros to be minus 3 and 2. So let us consider the general form of the quadratic polynomial It is ax square plus bx plus c, where a is not equal to 0. And here they have simply given the sum and product of the zeros. So we don't know what are the zeros of the quadratic polynomial. So let us take the zeros to be alpha and beta. Since their sum is equal to minus 3, alpha plus beta equal to minus 3. According to the definition, it is equal to negative of coefficient of x divided by coefficient of x square, that is minus b by a, and their product is equal to 2, which is equal to c by a. So from the above two equations, you can easily observe that a value is equal to 1 and b value equal to 3 and c value equal to 2. So by substituting the a, b and c values, we will obtain the quadratic polynomial to be x square plus 3x plus 2. We can also cross verify it to check whether the polynomial what we have obtained has the zeros whose sum and product are equal to minus 3 and 2, right? So, and the constant multiplication of this quadratic polynomial what we have estimated will also satisfy the conditions which were given in the question. So by simply multiplying the quadratic polynomial what you have obtained by a real number, again it will satisfy the conditions, right? So now let us verify this. The quadratic polynomial what we have obtained is x square plus 3x plus 2. So if I multiply this quadratic polynomial by any real number, say k. So let me take that real number to be 2. You can take any real number. So the polynomial what I have obtained is 2x square plus 6x plus 4. By multiplying any polynomial by a constant will not change the degree of the polynomial. So if I try to factorize this polynomial, I will get 2 into x plus 1 into x plus 2. So for x equal to minus 1 and x equal to minus 3, the polynomial will become 0. Therefore, the zeros of this polynomial 2x cube plus 2x square plus 6x plus 4 are x equal to minus 1 and minus 2. So now let us check the relationship between the zeros. So the addition of the two zeros, let me take the zeros to be alpha and beta. So alpha plus beta equal to minus 1 minus 2 is minus 3, and the product of the two zeros are 2. So thus the conditions given in the question are get satisfied for the polynomial k into x square plus 3x plus 2. So in the place of k, you can replace it with any real number, right? Now, let us consider a cubic polynomial. Here they have considered p of x equal to 2x cube minus 5x square minus 14x plus 8. So, for x equal to 4, minus 2 and 1 by 2, they are getting the polynomial p of x to be 0. Now if they verify the relation between the zeros, that is sum of the zeros and product of the zeros, they are getting the values to be equal to minus of coefficient of x square by x cube, and product of the zeros is equal to minus constant term divided by coefficient of x cube. So let us verify that. So here they have considered the sum of the products of the zeros by taking 2 at a time. So here the zeros are 4, minus 2 and 1 by 2. So by taking the product of two zeros at a time, they are getting the value to be equal to minus 14 by 2, which is equal to coefficient of x divided by x cube. So in general, for any cubic polynomial ax cube plus bx square plus cx plus d, where the zeros are alpha, beta and gamma, we have the following relations. Please note it down. The sum of the roots will be equal to minus b by a, that is negative of the coefficient of x square by coefficient of x cube, and the sum of the products of the roots taken 2 at a time will be equal to c by a, that is the coefficient of x divided by coefficient of x cube, and the product of the three roots will be equal to minus constant divided by the coefficient of x cube, right? Fine. Moving on to the example 5, verify that 3 minus 1 and minus 1 by 3 are the zeros of the cubic polynomial, They have given one cubic polynomial and then verify the relation between the zeros and the coefficients. So in order to verify the given number is a 0 to a polynomial, we have to simply replace the variable x by that number. So you have to replace x by 3, minus 1 and minus 1 by 3, and you have to check whether the values are equal to 0. So in all the cases, they are getting the answers to be 0. Therefore, 3, minus 1 and minus 1 by 3 are all zeros for the given cubic polynomial. Now we have to verify the relationship between them. So if we find the sum of the three zeros, we are getting the value to be 5 by 3. So according to the above expression, the sum must be equal to negative of coefficient of x square divided by coefficient of x cube. So in our example, the coefficient of x square is negative 5 and the coefficient of x cube is 3. So the answer should be minus 5 by 3. But we are having 5 by 3. But it should be negative of 5 can be written as negative of negative 5, which is nothing but negative 5 is nothing but b, so minus b by a. Similarly, if you multiply the zeros by taking 2 at a time and finding the sum, you are getting the final answer to be minus 11 by 3, where minus 11 is the coefficient of x and 3 is the coefficient of x cube. So we are getting the answer to be C by A, and the product of the three roots is equal to 1, where 1 is nothing but we are not having 1 in any of the terms. So what we have to do? In general, the product of the three zeros must be equal to constant term divided by the coefficient of x cube, right? So negative of constant term divided by coefficient of x cube. So here what is the negative of constant term? Minus of minus 3. So minus of minus 3 divided by 3 will give you the answer 1. So thus we have verified the relationship between the zeros and the coefficients of the terms in the given cubic polynomial, right? Moving on to the exercise 2.2, question number 1. Find the zeros of the following quadratic polynomials and verify the relationship between the zeros and the coefficients. So let us discuss one by one. So exercise 2.2, question number 1. First one, x square minus 2x minus 8. So we have to find the zeros for the following quadratic polynomial, and also we have to verify the relationship between the zeros and the coefficients. So since we have only quadratic polynomial, we have to check only the two relationship, sum and the product, right? So first let us determine the zeros. Factorizing the quadratic polynomial, we are getting the values to be x minus 4 into x plus 2. Therefore, for x equal to minus 2 and plus 4, we are getting the polynomial p of x to be equal to 0. Therefore, the zeros of the quadratic polynomial are minus 2 and 4. Now, let us verify the relationship between them. The sum of the roots alpha plus beta equal to minus 2 plus 4 equal to 2. So, this should be equal to minus coefficient of x divided by coefficient of x square, which is equal to minus of minus 2 by 1, which is equal to 2. Fine. Product of the two zeros, minus 2 into 4, which is equal to minus 8. This should be equal to constant term divided by coefficient of x square, that is constant term is minus 8 and the coefficient of x square is 1. So thus we have verified the relation. Question number 2, 4s square minus 4s plus 1. If you factorize it, By multiplying the coefficient of s square with a constant term, you will get 4. And if you multiply, you should get 4, and if you add, you should get minus 4. So minus 2 minus 2, by dividing it by the coefficient of s square, we will get minus 1 by 2. So the factors are x minus 1 by 2, x minus 1 by 2. Therefore, for the x values 1 by 2, comma 1 by 2, the given quadratic polynomial will have the value to be 0. Therefore, the zeros are 1 by 2, comma 1 by 2. Now let us check the relationship between the zeros and the coefficients. So alpha plus beta equal to 1 by 2 plus 1 by 2 equal to 1. It should be equal to minus the coefficient of s, that is b by a. Here b is minus 4, by a is 4. So the answer will be 1. Alpha beta equal to 1 by 2 into 1 by 2, which is equal to 1 by 4. This should be equal to constant term divided by coefficient of a square, that is a, that is 1 divided by 4. Fine. Problem number 3. 6x square minus 3 minus 7x. 6x square. So I am just rewriting it. So this is the quadratic polynomial given to us. Now we have to find the factors. Multiplying the coefficient of x square and the constant term, I will get minus 18. I have to find the roots, so that product should be equal to minus 18 and their sum should be equal to minus 7. So I will get minus 9, 2. So if you add, you will get minus 7. If you multiply, you will get minus 18. If you divide it by the coefficient of x square, you will get the roots to be minus 3 by 2 and x plus 1 by 3. Therefore, for the x values, 1 by minus 1 by 3 and 3 by 2, the polynomial p of x will become 0. Therefore, the zeros are minus 1 by 3 and 3 by 2. Now let us check the relation. Alpha plus beta equal to minus 1 by 3 plus 3 by 2. By simplifying them, you will get 6 minus 2 plus 9, that is 7 by 6. It should be equal to minus b by a, that is minus of minus 7 by 6. Alpha beta equal to minus 1 by 3 into 3 by 2, which is equal to minus 1 by 2. This should be equal to c by a. C is minus 3, a is 6, minus 1 by 2. So thus we have verified. Fourth one, 4u square plus 8u. This is also a quadratic polynomial. Though the constant term is not there, it is considered to be a quadratic polynomial because the highest power of the variable is 2. And now if you try to find the factors, you will get 4u into u plus 2. So for the values of u equal to 0 and minus 2, you will get the polynomial value to be 0. Therefore, 0 and minus 2 are considered to be the zeros for the given quadratic polynomial. Now let us check the condition. Alpha plus beta equal to 0 plus minus 2, which is equal to minus 2. This should be equal to minus b by a. Here b is 8. Minus 8 by 4 should be equal to minus 2. And alpha beta equal to 0 into minus 2, which is equal to 0. C by a. C is the constant term. Here constant term is 0. So 0 by 4 will be equal to 0. Fine. Fifth one, t square minus 15. So by applying the algebraic identity a square minus b square equal to a minus b into a plus b, we can rewrite this quadratic polynomial as t minus root 15 into t plus root 15. So for the t values minus root 15 and plus root 15, you will get the polynomial value to be 0. Therefore, these are considered to be the zeros for the quadratic polynomial. And if you check the conditions, you will get the sum of them to be 0, which is equal to minus b by a. Here b is the coefficient of t, which is 0. 0 by 1 equal to 0. And alpha into beta equal to minus root 15 into root 15, which is equal to minus 15, which is equal to c by a. C is the constant term, so minus 15 by 1, right? Sixth one, 3x square minus x minus 4. Minus 12. If I add, I should get minus 1, and if I multiply, I should get minus 12. So the roots are minus 4, 3. If I divide them by 3, I will get the factors to be x minus 4 by 3 into x plus 1. Therefore, for the x values minus 1, 4 by 3, we will get the polynomial values to be 0, and they are considered to be the zeros. And alpha plus beta equal to minus 1 plus 4 by 3 equal to minus 3 plus 4 by 3 equal to 1 by 3, which is equal to minus b by a. Here b is minus 1, so minus into minus 1 by 3, that is 1 by 3. Alpha beta equal to minus 1 into 4 by 3, which is equal to minus 4 by 3. It should be equal to c by a. Here c is minus 4 and a is 3. So thus we have verified all the conditions. Now moving on to the question number 2. Find a quadratic polynomial, each with the given numbers as the sum and product of its zeros respectively. So they have not given the quadratic polynomial, but they have given the relationship between them, that is the sum and product of the zeros they have given. Now we have to determine the quadratic polynomial corresponding to this conditions. So number 1, the sum is 1 by 4, and number 2 and the product of the zeros is given as minus 1. So question number 2, first one. So let alpha and beta denote the zero of the quadratic polynomial, right? Say ax square plus bx plus c with the condition a not equal to 0. And now they have given the sum and product. So alpha plus beta equal to 1 by 4 and alpha beta equal to minus 1. Fine. Now we have to simplify this and we have to determine the values. But from the above relation between the zeros and the coefficients of the terms, we can say a plus b equal to 1 by 4, which is equal to sum of the zeros will be equal to minus b by a, and alpha beta is equal to minus 1, which is equal to c by a. So from this what we can observe is, here we have a value to be 4, but here it is 1. So is there any possibility to convert this 1 such that a value will be 4? So minus 4 by 4, right? So from this we can say a to be 4 and b to be minus 1 and c to be minus 4. So the required quadratic polynomial is 4x square minus x minus 4, right? The second one, so I am directly writing the relation. So alpha plus beta equal to root 2, alpha beta equal to 1 by 3. So this should be equal to minus b by a. This should be equal to c by a. Fine. So by multiplying divided by 3, we will get, from this we can conclude a equal to 3 and b equal to minus 3 root 2 and c equal to 1. Therefore, the required quadratic polynomial is 3x square minus 3 root 2x plus 1. Third one, summation is 0, alpha plus beta equal to 0, product value is root 5 minus b by a, this is c by a. So 0 can also be written as, since here it is 1, 0 can also be written as 0 by 1. So from this what we can conclude is a equal to 1, b equal to 0 and c equal to root 5. Therefore, the required quadratic polynomial is x square, b term is 0, therefore x square plus root 5. Fourth one, both sum and product are equal to 1. So alpha plus beta equal to 1 and alpha into beta equal to 1. Minus b by a, c by a. So from this what we can conclude is a equal to 1, b equal to minus 1, c equal to 1. Therefore, the required quadratic polynomial is x square minus x plus 1. Fifth one, sum equal to minus 1 by 4. Product equal to 1 by 4. Minus b by a, c by a. So from this what we can conclude is a equal to 4, b equal to 1, c equal to 1. Therefore, the required quadratic polynomial is 4x square plus x plus 1. Next, sixth one. Sum is equal to 4 and product is equal to 1. Minus b by a, 1 by a. So from this we can say the value of a to be 1 and b to be minus 4 and c to be 1. Therefore, the required quadratic polynomial is x square minus 4x plus 1. Fine. So in the summary, they have given all the important points to be remembered. So what they have discussed here is polynomials of degree 1, 2, 3 are called linear, quadratic and cubic polynomials, and a quadratic polynomial with a real coefficient, they have given the general form, and the zeros of the polynomials are geometrically interpreted in such a way that the graph of the polynomial will intersect the x-axis at that point. So that point we consider to be zeros of the polynomial. And in general, a polynomial of degree n will have at most n zeros, and a quadratic polynomial can have at most 2 zeros, cubic will have at most 3 zeros. So in general we have stated that, and the sum of the zeros of the quadratic polynomial will be equal to minus b by a and product equal to c by a. And they have also given the relations between the zeros of the cubic polynomial. For quadratic we have only 2 conditions, whereas for cubic we have 3 conditions to be remembered. Fine. With this we have completed chapter 2. In the next video we will discuss chapter 3. And if you have any doubts, you can comment it in the comment section, and if you like the video, please click the like button and please share this to your friends, and please subscribe to the channel. Thank you.